Everyone out there in the live stream, welcome. Thank you for being here. Put your comments, thoughts, feedback into the live chat, and we'll try to make it part of the show. And with that, hello, Boris, Victor, Jonathan. You all ready to start the podcast?
Yeah.
Ready to go?
Yeah, thanks for having us.
Cool. Boris, Victor, Jonathan, welcome to Talk Python to Me.
Thanks for having us. Glad to be here.
It's great to be here with you.
Welcome, everyone.
Yeah. Hey, you all are doing really important work, and I'm super excited to talk to you about it. So we're going to talk about machine learning, how much carbon is being used for training machine learning models and things like that, and some cool tools you built over at CodeCarbon.io and that collaboration you got going on there. But before we get into all those sides of the stories, let's just start with yours. Jonathan, you want to go first? How'd you get into Python?
Sure. Yeah. Thanks for having us, Michael. My name is John Wilson. I'm a associate professor of environmental studies at Haverford College. I'm actually an environmental scientist, so I was brought in to kind of consult from the environmental side of this project. But I have a secret history as a computer science undergraduate back in the dark ages, learning to code on C, C++, and Java. So I was brought in to kind of like provide that environmental perspective on the project. And having a little bit of a coding background, despite how rusty it is, has been pretty helpful at thinking some of these connections through between computational issues and environmental issues.
Yeah, I can imagine. Did you find Python to be pretty welcoming, given like a C background and stuff?
Oh gosh, yeah. I mean, I learned back in the bad old days or not bad old days, I shouldn't say that. Scheme, things like that. A little bit more challenging.
That's one of the first languages I had to learn for like a few CS classes I took. It was like, we're going to start with Scheme, like anything but this. Give me something mainstream, please.
Yeah, sometimes I feel like the sort of like older person telling the kids these days about how we had to walk uphill both ways in the snow to learn programming, and it's much easier. And it's one of the things I like about Python is it's really accessible to people from different fields. You get into it from aspects of natural sciences, but even people who are like in the digital humanities are using it to for language processing and things like that. It's super flexible, which is really neat.
It's really impressive what people in those different fields are doing. How they can bring that in. Boris, how about yourself? How did you get into Python?
I actually discovered Python during my master degree, and I got a math teacher that introduced us to Python because he used Python for his own thesis, and I had one stuff to do, which was implementing RSA encryption, and I didn't want to do it because math was not my forte. So instead, I did some encryption inside images in Python, and I fell in love with Python.
Oh, fantastic. Victor?
I discovered this taking a data science class in, when was that? 2014, I think it was. So that's really, I really entered Python through the data science perspective. And then I took a course in general web development, and we used Django.
Oh, right. Nice.
And so it's been really like the main language I've been using. I was taught CS with Java and so on. So I was never a computer science fan. Like, I liked math. And I found Python to be really flexible in that regard. Like, you can do maths super easily without like getting lost in translation.
Yeah, one of the things that just came out is one of the new Texas Instruments, the TI-84 calculator. They have you can now program it with Python. So that's kind of interesting now that it's one of the old calculators that everyone's probably used going through math and whatnot is now sort of more in the modern space.
Yeah. I have a friend who. Sorry, go ahead, Boris.
I think my first program was on my TI because I was bored in math course and I cannot follow. So instead, I wrote some programs.
Yeah, that's not a terrible way to spend your time. All right, so let's go ahead and talk about the main. Get to the main subject here. So let's start by just setting the stage. There's an interesting article here that came out. This is not even that new. It's 2019, and it's in the MIT Technology Review. So, that gives it probably a little more than just some random blog says this. And it's got a big picture of a data center. And the title of the article by Karen Ho is "Training a Single AI Model Can Emit as much carbon as 5 cars throughout their lifetime." So that sounds pretty horrible. But we also know that machine learning has a lot of value to society, a lot of important things that it can do. So here's where we are, and this seems like a good place to start the conversation for what you all are doing.
I think I have a mixed feeling about this article. I think one of the great things it did is raise a lot of attention and awareness about this topic. I think a lot of approximations were made, and it was not, the goal here is not to criticize authors, but rather to say that in the meantime, things have evolved and our understanding has, I think, been a little more precise. Also,
maybe because people are building tools that measure it instead of estimate.
So there's that, definitely, and we hope that helps. But it's also like one of the things you need to put in perspective is that the kind of model they're looking at is not necessarily your everyday model. Someone can just train on their local computer, or even in academia, it's hard to get your hands on such large clusters and the number of GPUs used and so on. So like, I just want to put that in perspective, that even if those numbers were accurate, and they are not, but I mean, it's a ballpark. It's not like every data scientist you'll meet and every AI researcher you'll meet is going to have something in that like level of complexity that they train every day.
I have over here a sim racing setup for some sim racing I do, and it has a GeForce 2070 in it. It would have to run a very long time to emit this much carbon, right? Like if you got to have the necessary money and compute resources to, even get there, right?
Yeah, like the number, I don't remember exactly the setup that they're looking at in this paper, but like typically the modern language models that you hear about, like, OpenAI has an NLP model and like GPT-3, and it's that number of billion of parameters. Like, they train those things on hundreds and hundreds of machines for a very long time. This is not something you can do easily. It costs millions of dollars in investment upfront, and then just using those things is super expensive. So while I think we should be careful, it's not like the whole field is like that.
Yeah, that's a good point. That's a very good point. I recall there was some cancer research that needed to answer some big problem. And there was an article where they spun up something like 6,000 virtual machines across AWS clusters for an hour and had it go crazy to answer, some protein folding question or something like that. That would use a lot of energy, but it's extremely, extremely rare as well. On the other hand, if you create that model and it solved cancer, well, people drive cars all the time for less valuable reasons than curing cancer.
Yeah, and I think just to build on what Victor said, I think there was something really valuable about this article coming out. I think for a long time, there's been attention that's been paid to the sort of environmental toll of supply chains in computing. People have talked a lot about where minerals come from. Yeah. And I think the one of the things that was really interesting about this article was, with the approximations, it got people thinking about the question that kind of animates our collaboration, which is, when you're doing any kind of energy intensive computational issue, you might want to think about where your electrons come from. What's actually powering the hardware that you're using to do this. And I think this article did a really nice job of like focusing attention that there are some really energy intensive projects that in particular ways, in particular, if they're located in particular locations, they can have a really large environmental cost that isn't really transparent to the user or the person training the model.
Yeah. Well, I don't want to go down this road just yet. I want to keep talking about the more high level a little bit. But, if the people who did this very expensive model, if they just said, I'm going to pick the closest AWS data center to me, that rather than let me find the data center by just flipping a switch and say, no, maybe the one up in Prineville, Oregon by the dam would be better than the one by the coal factory, for example, right? Like that's something they could easily do, and it maybe doesn't change anything for them, right?
Yeah, it's
definitely.
not always the case, because when you have, for example, health data and so on, like there are legislations, but definitely, like if you can, like, and there's more than just the money at stake here, and it's probably going to be a marginal change, because the prices tend to be not equal, but kind of uniform still. I think it's another decision item.
Yeah. Boris, you got any thoughts on this article before we move on?
Yeah, I think it came with a good to highlight a serious issue, and if people want to improve it, as most of my manager told me, if you want to improve it, you must measure it before. So we are there to give us a start of an answer to and give then action how to improve the CodeCarbon emission on training models. Hopefully to not train less models, but train better models.
Yeah. So one thing, yeah, go ahead.
Yeah, just one little thing. And I maybe caricaturing, but I think the intent is the same. I think, for example, this is part of what the recent Google paper led by David Patterson on training neural networks and their environmental impact. This is one of the things they say, and it's quite a dense paper and a lot of metrics and so on. But one of the things they say is, like, if you don't want people caricaturing your numbers and putting approximations out there, well, you better publish those numbers yourself, right? And you need tools to do that. So if you're Google, or if you're close to the infrastructure that you use, it's easier. It's even better if you have access to the plugs. But that's not the case of everyone, right?
Right. So you're saying if you could put like something to actually measure the electricity going through the wire instead of some approximation, you're in a better place to know the answer. Yeah,
definitely. That's where I think, and we might be a little ahead of your schedule, but we might go there still, which is like, that's where CodeCarbon comes into play, right? This is why we want to create this tool. This is a user-facing product, right? And I think it's very important to highlight that it is not intended to be the solution for a data center. This is not something that we think should be deployed as a cloud provider, or if you own your own infrastructure. If you want to have centralized number, there are alternatives out there. Things like scaffold, scaphander. I don't know how you say that. It's a French word. Anyway, it's out there on GitHub. You can find it by just looking this word. But like the goal here is, like, as a user, what can you do if you don't have those numbers? Right? Do you do nothing, or do you try to at least have the start of an estimation, and maybe start the conversation with your organization or your provider?
Yeah, fantastic. And you guys are putting some really concrete things out there for Python developers. Two quick high-level comments. One, Corey Adkins from the live stream says, would it be the same or worse for quantum computers?
Okay, I'm going to talk out of my depth here. So the first, like the best answer I can give is I don't know. And then to go beyond that, like, my understanding of quantum computers is that they do very different things, and you can't just compare the computations made on classical computers with the things quantum computers are intended for. I think intrinsically, because of the state of that technology, it is extremely energy intensive, just because you usually have to pull things down to a few millikelvins or something like that. So that may be transitory. I'm not sure. I don't want to talk too much about
I don't know about that either.
I was thinking,
I was thinking the same thing. You know, just yesterday, Google had Google I/O, and they talked about building clusters of qubit sort of supercomputer type things, and apparently they've got to cool it down so much that it's some of the coldest places in the universe inside those. So on one hand, if quantum computers can do the math super quick, it doesn't take a lot of time to run them to get the answer. But on the other, if you've got to keep them that cold, that can't be free.
Mm-hmm. But it's a very particular kind of math. right? And not all problems are translatable from the classical formulation to a quantum compatible formulation. And I think, I'm not sure, I think there are problems that we can solve easily on our classical computers that would be very hard, if not theoretically impossible, to run on quantum computers. And it's like, it's a different tool and it's not intended for the same problems. So I think it's hard to compare.
Yeah. Makes sense.
I will even say that you will still have some part of the model training that won't run on quantum computers, because that doesn't make sense, like pre-processing data, getting data from your different data source, mapping them to a common format, exporting your model, creating Docker images, servers. That there will still be part of the model training process that won't run on those quantum computers.
Yeah. Another thing I think is worth pointing out is it's the training of the models that is expensive, but to use them to get an answer, it's pretty quick, right? That's pretty low cost.
But it depends on what you're using it for, right? So if you have a user-facing model that's going to serve thousands of requests per second, then deploying it for a year might be more energy intensive than training it for 3 days. We all know, like, the machine learning lifecycle is not just like you train one model and you succeed and, well, hooray, right? You usually have a lot of iterations, building the models, looking for hyperparameters and so on. But even if that takes 6 months and your model stays online for months or years and serving thousands of people, it's not obvious. It might even be worse, not worse, more energy intensive to infer.
Yeah, I guess it depends how many times you run it. Another thought, there's a lot of places creating models, like you talked about, was it GPT-3, and whatnot, that are training the models and then letting people use them. Do you see that as a thing that might be useful and helpful, as having these pre-created, pre-trained models? Like, I know Microsoft has a bunch of pre-trained models with their cognitive services, and Apple has their ML stuff like baked into their devices that you don't have to train, you can just use. Are the problems being solved and the data being understood usually too general, or is that something we can make use of?
I think pre-trained models has the advantage to keep, as you are training a model once, the cost emission of the model during training is amortized for each usage. So more user you have, the more the part of the training emission is low. But usually you still have to tune the model a bit, so you still have to train it, and you're using energy even for prediction. So
I think it's I'm gonna also do the transition to throw the ball to Jonathan for something I think is we shouldn't forget when we talk about like these gains in efficiency, which is like the Jevons paradox, and like the fact that if you create something that is cheaper to use and more people use it, then the overall impact is it lower. Like, and I think this is something we tend to forget when we talk about like massive improvements, or not even massive, just like this is something that is, I think, hard to grasp and anticipate when you think about technological advances under the constraint of climate change. But this rebound effect, I think, is something we should plan for, and not just think, well, if you have cheaper models but more people can use them, I think it's not that obvious that it's an overall gain in terms of energy. Like, then we can talk about all the societal consequences and the advances in cancer research, for instance. But I think it's really hard to have a definitive answer.
Yeah, just to build on what Victor said, it really is a difficult. I mean, this is a classic environmental conundrum, right? When you the classic example of the Jevons paradox is, adding more roads leads to more traffic because more people believe that there's more space for them to drive, and so you've seen this over and over again in all sorts of different contexts. That when you build these tools, more people will use them, and that can end up costing more than not building them in the first place. So I think this is something to really be aware of, as we're sort of democratizing these kinds of tools. There's a real pro here. There's some real strengths of having these tools, easily accessible and that can be used. But one has to worry about the potential costs of, having, all these tools being employed, in particular being employed in all sorts of different kind of sub-energy grids around the world. Not all grids are, connected up to solar panels. Many are connected, to coal-fired power plants, and
we
that
can
outweigh that cost.
It's not today, is it?
Yeah, not yet. One would hope, but maybe soon.
One thought about pre-trained model is usually they are trained for more diverse usage. So I would think that they tend to be larger than model trained, especially for a single usage inside a single company with a single type of data. So I would say they are likely bigger, so they use more energy to train and to use, but by how much I couldn't say.
Yeah. Well, I think the paradox that you all are speaking about, one of the ways we could see that is just the ability to use machine learning to solve problems is so much easier now. That what used to be a simple if-else runs in a microsecond is now a much more complicated part of your program. And so, yeah, there's got to be just a raising of the cost there. Now, before we make it all sound like machine learning bad for the environment 100%, there are good things, Google, like I said, Google I/O was yesterday, and they were talking about doing the navigation so that taking into account things like topography, speed, and whatnot to actually try to optimize or minimize gas consumption with the directions they give you, right? And if they could do that with a little bit of computer code to save a ton of CO2 out of cars, like that's a really big win for ML.
Definitely. And I think the reason why we have started with the online carbon emissions on our side at Mila in Montreal, and Jonathan and colleagues at Haverford with energy usage, and then we came together for CodeCarbon. It's not to say that machine learning is bad. Like, just as most technologies, it's technology and it depends on how you use it. But where we're going as societies under the constraint of climate change can't leave any field out of questioning themselves of how they use their resources. Yeah. So it's something you can't leave out of the picture, which doesn't mean that you can't use it. It's like you have to think about it, and we can't have a single rule for everyone. It's just you have to take that into account, and you can very well make the decision that it is worth it. And in many cases, it will be. Sometimes maybe not.
But be conscious of it. Yeah, for sure. All right. So I think that brings us to your project, CodeCarbon. You mentioned it a couple of times. So looking in from the outside, it seems to me like the primary thing that what you guys have done is you've built some Python libraries, a Python package that lets you answer these questions and track these things, right? And then a dashboard and data that will help you improve it. Is that a good elevator pitch?
Very good.
Fantastic. All right. So
you
tell us about CodeCarbon. Yeah, sure. Not busy.
We don't have any money though.
Oh, good. Yeah, I'll be right there. No, but I think it's a great cause. And so tell everyone about it.
Thank you for the opportunity. I think one of the reasons we came together was we all know that in the machine learning lifecycle, a lot of the computations you just forget about because there are so many experiments that you run. Like, say you have a project and you're going to work on it for 3, 6, 12 months. How many experiments are you going to run? How many hyperparameter searches are you going to run? It's a very important problem. I think this is also something that is central to Comet.ml, which is the company where Boris works at, and they manage experiments, and I use that in my daily work. And I thought, well, we need something similar to track the carbon impact. It can't just be about the metrics. It can't just be about the images you generate because you're training a GAN, for instance. So how do we go about this? And well, because Python was is I think the go-to language for AI research and development also, although in very optimized settings you might want to go away from that. But we thought, well, we need to do something that is going to be plug and play, so it has to be Python. It has to run in the background. It has to be light, and it has to be also something that is versatile in that it is not only about your just getting yet another metric, but it's also about understanding what it means. It's about also education. It's about education for yourself, but also maybe for other members of your organization, the people who might say you work in a company and you're thinking, well, I have hundreds of data scientists. Like, this is not marginal. I want to have an estimation, and if estimations are not good enough for you, well, contact your provider and maybe have a watt meter plugged in somewhere where it matters. That's not my expertise.
No,
that's basically the idea.
Yeah. Well, I think plugging a watt meter somewhere, that used to be a thing that you could do, but now it's, Amazon or Azure or Linode or whoever, they're not going to let you go plug it into their data center. And if you did, there's probably a bunch of other things happening there, right? Direct access to the compute resources is just hard to come by.
Yep.
Exactly. This is a very big constraint for us, right? This is, and I expect we'll get into a little more details about that. But this is why you need to understand CodeCarbon as a tool to estimate things and have approximations, and we use heuristics. And basically, if a consultant is having you pay for carbon offsets based on those kinds of numbers, you shouldn't pay, because that's not the point.
Yeah. It's really about giving you the information. One thing I like about what you're doing is you can recommend other areas, like we talked about. Like, you could switch to this data center, and then it would have this impact, right?
Yeah, I think it's part of the educational mission. It's like, we all know, or at least I wish we all knew, or we want everyone to know. I don't know how to put that, but that it's the climate change is a very serious threat, and being conscious about your energy usage and your consumption of resources in general is one thing. It's very important, but then I think you can't just leave people out there with that feeling of guilt, and there has to be actionable items. So changing your region is probably the easiest thing you can do, especially in the age of the cloud, and at a time when basically moving your data across continents is about ticking a few checkboxes on a web interface, right? So
yeah.
Yeah, I think just to pick up a little bit on what Victor's said here, is that this is the educational part of this is a very important part of the CodeCarbon project, because we know, as we have been involved in this, that answering this question, like, what's the CO2 footprint of my computational work, is actually a very, very difficult question to answer. And it's opaque for a variety of reasons. It's opaque because the way that the energy industry deals with CO2 emissions is pretty opaque unless you know the language of how they express this. And it's also difficult to understand, when you are able to make the calculation, well, what does that mean? How does this, what's 1 gram of CO2 emitted relative to, say, everyday activities? So one of the things that we've tried to do as part of this dashboard is simplify those 2 steps for people, because we've been approached by people, via email, via Slack, and we know we're not the only people concerned about this. And so this is just a way to help make these approximations both visible, but also kind of comprehensible, and put it in the context of human activities.
You're right. There's a lot of layers, and companies that run the clouds, they are trying to be more responsible with their energy, but you don't know. A lot of times you don't know if this data center, US East 1 and AWS, how much energy from different sources is that actually using? How much have they actually, built their own solar and wind? We don't know, right? But you get a better sense using your tool. You've got better data than the random person who just kind of estimates, well, they're They're doing some
Also-
stuff, so it must be fine.
And another important thing, I think, is, and Jonathan is much more an expert in that than I am, but like not emitting is very different from offsetting in whatever way, Rex or whatever.
Yeah, that's a good point.
Your emissions and our atmosphere, our climate has inertia, and the expected compensation in 5, 10, 20 years of your current emissions, those are two very different things, right? And it's much easier to put carbon in the atmosphere than taking it away from it. And so
Yeah.
I think it's not just because you read that Google and others, Microsoft, are carbon neutral, which comes from compensations of many forms, doesn't mean no carbon was emitted. Right?
Yeah, just to build on Victor's point again, there's decades of research in sort of what you'd call, environmental psychology, showing that, explaining to people the consequences of inaction or of diffuse environmental costs to a particular action causes long-term behavior change. And I think, one of the things that's been really exciting about seeing the machine learning and AI communities kind of like grapple with this question in a very public way is we've started to see articles of, pressure being put on organizations to, why don't we have more green energy infrastructure, undergirding our work. And so, the speed at which this has become, a public conversation is really heartening, as somebody who's been working in the environment for quite a bit of time.
Yeah, I would say it does seem to be getting a lot of attention, which is good. It's a big problem, but attention instead of just head in the sand is a really big deal. Like we've been driving cars for a long time. We've been flying planes for a long time. And there's a lot of like raised trucks with super big wheels with, dual, cold stack pipes on them, right? Like that's I can't speak for everyone that gets a truck like that, but I feel there's a lot of times when we have these conversations, people are just like, well, this is so horrible and so vague that I'm just going to live my life and enjoy it because I seem to not be able to do anything anyway. So I might as well have fun instead of not have fun while things are going wrong. Right. Like that's kind of that psychology. Right. And so I don't know. How do you all deal with that?
And it's also something that's like when it's not before your eyes, it's much more difficult to answer, to understand and to respond to. And I think this is part of what we're seeing today with decades of activism is like hard facts are not enough to convince humans, and to some extent it's also a good thing, and it has, I think, it has value in our recognition, but it also has this downside that it's just because you say a number to someone, if they don't understand it, if they don't see it for themselves in their everyday life, it's going to be very hard to understand. So until you have used something like CodeCarbon, like I code every day, I train models every day, and I train a model for 5 days on a GPU in Quebec, right? That's my daily life basically, and some might find it dull. I like it. Anyway, that's not the point. I mean, until you have that and you're like, oh, this is what I do, those numbers start to make sense.
Yeah.
And even if you have numbers for your day-to-day, that doesn't seem that much, like thousands of grams or kilograms, but once you sum all the emission for all the model trained, for all the machine learning teams, for all the machine learning data scientists for a company for a year, or even for academia, that start to get, depending on your size of the company, of course, that start to get sizable, and you might want to take a serious look at it.
Yeah. All right. I want to dive into the code and talk about this, but I guess maybe speak really quickly to, I work at a company. We make shoes. They want me to use ML to figure out how to get, better behaviors out of the materials for track runners or whatever. So I do that. That company, how do I get that company to say, yes, we should measure our scientific data science work, and we should offset it. Like, there's a lot of layers between the people who care about shoes and sales and people who care about machine learning carbon offsets.
My personal understanding of the situation is that empowering individuals with tools and numbers to convince organizations is part of our mission. So if what the person in charge, whatever their role in the organization, thinks that in order to have an estimation of their carbon impact, they have to find a consulting firm, pay people for 5 weeks, and if they think this is the process, they're going to be reluctant. I can understand why. If you have a plug and play tool that even you as the evangelizer, if that's a word, but you get the idea. Even if it doesn't cost you much to try, right? I mean, the way we want to build this thing is just like one import and a couple of lines.
So let's talk about the code. I think maybe the answer, maybe an approach that you could have there is we'll run something like this on all of the training that we do, and then we're going to report up our division in this company generates this much carbon. So if you care about carbon, you need to take that into account.
Yeah, I think that's a good starting point. I think as we can see today together, I mean, those conversations are hard and long, and it's not easy to understand all that matters, and you may need that consulting firm in the end to help you understand what's at stake in your whole value chain. But you got to start somewhere, right? And if you're an individual and you want to change your organization, well, I think if you want to have an impact, those kinds of tools should be easy to start with. And then, as we've said, it's not enough and it's not precise enough. And then there are other steps you can take. But you need to get the conversations going and start it.
And to start that, you got to start measuring. So in order to do that, let's talk about the code. It's literally 4 lines of code. That's all you got to do. You pip install CodeCarbon, and then from CodeCarbon, import emissions tracker. Create one, tracker.start, do your training, tracker.stop. And that's it, right?
Right. And with the decorator solution, it's 2 lines of code.
Yeah, with the decorator, you can just put a decorator on a function, and then basically any training that happens during that will be measured and then saved to a CSV file, right?
That's it.
That's correct.
And if you think a context manager should be implemented, well, you're welcome to create a PR. It's going to be super easy. Everything is already there.
Yeah, exactly. I can already see it in my mind with emissions tracker, as tracker. Cool. So it creates one of these CSV files, and then what?
So there are a bunch of things that happen. If you want to, like the 2 big steps are, one, you look for the hardware you understand, like CodeCarbon understands, then you track those, you measure the energy consumed, right? And so you have that, basically you measure the energy. And then next step is, well, how much carbon does this energy has emitted, energy emitted? And so you need to map the code to your location.
Right. And do you do that by just like a get location from IP address type of thing? Or
exactly.
Something like
so
that?
You can either do that or provide the country ISO code. For a couple of countries, Canada and the US, we have regions below the national level. Another thing that you can actually do is, well, it's not going to help you with the location, but it's going to help you with the carbon impact. Is we can ping CO2 signal, which is an API that is being developed by the Electricity Map initiative, group, organization, company, whatever their status. And so that's going to help you have an exact estimation at that moment in time, depending on what data they have of those computations. Otherwise, we need to have your country code, and we're going to map that to historical data.
This CO2 signal, this is new to me. What is this?
I think you'd better look at then the
look at the map.
Exactly. Yeah. So they have products, they have predictions of carbon emissions and so on. But that's basically, it's an initiative. The organization is called Tomorrow. And the goal here, at least with the electricity map, is to gather data about carbon intensity and the energy mix of countries through the forest of APIs and standards countries have for countries and companies and have for that kind of thing. So you can see that, for example, in Canada, not all, or in the US, not all regions are going to work similarly, and some regions might not even provide that kind of data in the open.
Yeah, that's too bad. Yeah, but it's really different depending on where you are, and just even the US, right? Like in the Pacific Northwest, I think it's like very high levels of hydro. Southeast, there's a lot of coal still. Like, it's not just what country, it's even like maybe a little more granular than that, right?
Yeah.
At least for large places.
Yes. And also, as you can see, I think this is also a very interesting map, because you can see that energy grids are very different from the grid that like nation, state, whatever is after that, right?
Yeah, county, city, all that.
County, city, all of that. Like you can see, for example, the one that spans something like Iowa to or I was thinking 880R, like this thing that goes from Montana to Texas or something.
Yeah, that doesn't look like any state I learned in school.
No, but it's probably a unified grid for some reason, because providers got together under some constraints.
Yep. Yeah, exactly. So when I'm looking at this code here, I run that, and then I get this map, and it could give you recommendations on the cloud regions, right, and where you might go. So, for example, CA.
So you're on the left. This is something that we might want to change, right? The UI of this thing might not be obvious, but you're on the left. This, I just want to make this clarification, because I sometimes forget. I'm like, where was this thing run? But it's actually, you run on the left, and we show you how it could have been different somewhere else.
Yeah, so if I pick, say, US West 1 for AWS versus EU West 3, you can see the relative carbon offset or production, how bad that was or how good it was. Yeah. And these comes from those reports generated out of that CSV file.
Exactly.
That's correct.
So I just want to be clear about how the data was gathered, because that's a very important topic. So we still need to update the data for GCP, Google Cloud Platform, because they recently released those numbers. But for most of those locations, we had to make an assumption. The assumption was that the data center was plugged to the local grid. So if a data center is in Boston, we assume the data center uses the same energy as Boston's grid, which might not be the case, right? Many providers now have their own solar panels and whatnot, so that might not be the case. And so, but unless they release those numbers, and I can find the link, I'll share it with you. Unless we have those numbers publicized by the providers, I mean, there's only so much we can do, right? So
yeah, well, here's a call to action for those who haven't released it. Get on it, right?
I think it was part of Jonathan's message earlier, which is like, there are so many layers and so many of them are opaque. Like, that's part of I think, our responsibility as users. I don't like to put too much weight on individuals' shoulders, and I think structural changes have a much wider, much more potential. But I think it's still interconnected, and if you can do something about it, well, you should.
Yeah, let's talk a little bit about running it. So when I go over here and I say start and then stop, like, how do you know how much energy I've used? I mean, I know once it leaves the computer, like, there's a lot of assumptions and various things like we talked about, but how do you estimate how much that code has taken?
That's a very good question. And Victor, can I answer this one?
Oh, yes. Sure.
Okay.
Please.
So when you are training and you're using running a machine learning program, you are mostly using GPU, and you are mostly using NVIDIA GPU. And thankfully, NVIDIA has a nice SDK to get at a given time the current estimated, but plus or minus 5% energy usage of the GPU. So we
really? Okay. So it's not like you're saying, oh, it's a 3070 super and it must be pinned CPU wise or GPU wise. So let's just assume this much time times this kind of computer. It gives you more narrow, exact measurements. Okay. Fantastic.
But we still get the energy consumption from all GPU. So if you are training multiple models, we might get higher or lower energy estimation. I'm not sure there. So that's for GPU. For CPU, we are supporting Intel, and we have several ways of doing that. Either we get a measurement at the beginning of the training and at the end, and we get the total energy usage between the two, so we can get the difference. Or we can also regularly get the immediate usage, I think. We are working to add memory usage, because even if GPU and CPU are the topmost resources that you use for multi-gigabytes server, it's tend to be not negligible. And once you
probably
get
disk as well. Yeah.
Yeah, disk. Everything takes energy. The goal is to focus on what takes most of the energy, and how easy it is to get that consumption. So you get all of that either during the training frequently or at the beginning and the end. In addition, we get the duration, and we detect if you're running in a data center or not. So in case we don't have access to anything, like you're running on AMD GPU on an AMD CPU on Windows, we can still give you an estimation based on the duration and on your estimated location, or if you are running inside a data center or a specific location, we can also get a more precise estimation for you. And we are measuring what, like, energy usage, and then we can use our data to estimate again, it's estimation of estimation, the CO2 emitted for that usage.
I don't know how deep you want to go into how it works, but I do want to point out.
Give us a little look inside, yeah.
Yeah, given that it's one of the most difficult area, I think I also want to use your platform to call for help, which is it's actually the low-level inner workings of CPUs are hard to understand. At least for me, I have a background and I'm a researcher, right? So it's an area where we
not necessarily a hardware specialist, right? Writing on hardware, yeah.
Exactly. And so, for example, like the way we read the energy consumption of Intel CPUs, the GPUs, as Boris said, have, at least NVIDIA's GPUs, have this driver that we can ping, and NVIDIA SMI is, or the PyNVML package is very useful because we can just ping this and not care about how it's done and trust NVIDIA and use that number. But for the CPUs, it's much more complicated. The reason is that what happens under the hood is modern Intel CPUs, under the right settings, write actually their energy usage in millijoules to a text file. It's the RAPL interface, and they write to a text file the number of millijoules they have consumed since, I don't know when, since they were turned on, or the 1st of January 1970, or whatever other random date. What matters is that, and we look at the difference anyway. But those numbers are written by the CPU socket. So let me give you an example. In the academic setting where I work, we have shared clusters. I can request part of a node, and I'm going to request one GPU and 20 CPUs to do my computations. But what I saw looking at the RAPL files is that there are 2 sockets of 40 CPUs. Like we have 80 CPUs per node and 2 sockets of 40. So there's no way
so
to
your
read from the
granularity
REPL
is
file.
40. Yeah.
And like the CPUs that are allocated to me might change over time, maybe not, depends on the resource manager. We use Slurm, and those CPUs will be split across those 2 sockets. And so we have that level of problems too, right? So the high level, you're working in a dedicated environment and it's only your program, then REPL is perfect and we couldn't have jumped for something better. But it does not allow us to go to the core, let alone the process granularity of power consumption. So I just want to put like a big warning here. And one of the things that we need to look into, and it's very hard, and there are no good numbers, maybe even what I'm going to say won't make sense, but the only solution we have left is there some kind of heuristic to map the CPU utilization to the energy consumption, basically, because otherwise we're never going to be able to attribute your processes and sub-processes CPU usage to watts, basically.
Yeah.
Because of this REPL setup that is written by a socket. And I've talked a little to people who understand this way better than I do, and they thought this endeavor was very risky. And they were pessimistic. But
and you're like, but what else do we have to work with, right?
Yeah. And so I think the next thing is like, we're going to need to get our hands on hardware, have it run, and see how bad it is. Yeah. And it's going to be one setup with one mode for the compilation of the math libraries I'm going to use to benchmark and whatnot. Like, there's only so much we can do if the hardware providers don't tell us more.
It would be nice to see operating systems and then the hardware providers as well, allow you to access that information, right? Like how much voltage how much am I currently consuming with just this process, right? You don't want to profile it, because if you profile it, you'll be like 50% of the problem, right? And you'll slow it down and people won't want to touch it. So yeah.
I've seen and talked to people at the Power API and PyJoule initiatives. And even they, from what I remember, explained that even if you had total control on the hardware, on the software, or the hardware, well, both of those things are going to be so dependent on the way you compile the libraries you use, and a number of other facts that even the very definition of those things that we're looking for is not obvious.
Or whether it's Linux versus Mac OS versus Windows, it's got to make a difference.
It all matters. And the reason why I think it's still worth looking for an approximation through CPU utilization, even if it's a bad proxy, is it's all bad proxies. So why is it like, it doesn't matter if you're precise to the millijoule on your CPU if your uncertainty around carbon emissions is huge, right?
Yeah. Otherwise, you end up with something as much carbon as 5 cars, right?
Yeah. And so
like we could get it down to 2.1 or 2.2 cars. Come on, let's go with that.
No. So it's really a very complex endeavor.
Yeah. Yeah, absolutely. So it sounds like it runs on multiple platforms. It sounds like it supports Intel.
At least.
Yeah. So Windows, Linux, Mac OS. I'm sitting here recording on my Mac Mini M1 Apple Silicon. Can I run it here?
Yeah. You would need to install the Intel Power Gadget, restart your computer, allow specific security permissions.
It's not an Intel CPU. So I'm guessing we will be back to the simple heuristic based on the
we realized actually the Intel Power Gadget also tracks some AMD CPUs. Like we had a user say like, oh, you don't seem to support AMD, and then they still installed the Intel Power Gadget. I don't know why, but they did, and then it worked. So I'm like,
Interesting.
I'm not sure how this thing works.
So Intel, AMD, but maybe not Apple Silicon.
Yeah,
Mm,
I'm not sure.
I don't think
Yeah.
so.
Okay, well, probably most people won't be doing training on that.
I
Anyway,
think the Silicon app, the Apple Silicon platform has a dedicated course for machine learning. No,
It does have, I think, 16 ML cores. Yeah, so yeah, maybe they are. They're coming out with the Mac Pro, which is supposed to have many cores. So maybe that'll be where people do it, more of it.
so if
Yeah,
Apple is hearing us, send us a Mac Mini and we'll work on
Exactly.
improving the tracking.
And
of,
one Mac Minis for all three of you, the whole team. Come on, let's send it along. Make it happen.
You have my Twitter handle. Send me a message.
Fantastic. All right. Let's see. Before we move on, quick question from Brian in the live stream. Other than moving to different data centers, what are some of the highest impact changes people can make? Different training methods and so on. And by the way, that also leads exactly into where I was going. Thank you for that. A very timely question. Like patterns and things you can do. Let's talk about that.
One of the things that we wrote in the quantifying the carbon emissions of machine learning paper, it's on the website, is, well, there's hyperparameter searches. Like one of the worst things you can do, both in terms of pure ML performance and carbon emissions, is grid search, for instance. So maybe just don't do that. If you're lazy, just do a random hyperparameter search, or if you don't have a good metric, or use Bayesian optimizers and so on to look for those hyperparameters. Another thing that is not mentioned in that paper, but I think is still very important, and that cycles back to one of your first questions about inference versus training, is there are many methods out there. Pruning, distillation, quantization, all that zoo of tools and techniques and algorithms to optimize your model. And if you're happy with your current model, chances are there are many techniques out there that can reduce its size and computational complexity by multiple factors. So if you're going to put a product out there with hundreds, thousands, millions of inferences, maybe just think about that. I expect people who deploy such tools do think about that. If you're like deploying a tool for millions, I mean, it's in your interest to think about it, because it's also
They probably
be cheaper.
think more about it in terms of just time, time to train, time to get an answer. But that also is exactly lining up with energy consumed. So, CO2 reduction comes along for the ride.
Yeah, it's often the case that if you invest in ecological solutions, they are going to end up being economical too.
Yeah,
Jonathan, it's more of your area.
Definitely.
Maybe that's
Definitely. I mean,
to you.
I couldn't underscore that more. I think something that I think that has come out of our results that we've seen is that there's not a strictly linear trade-off between energy usage and accuracy. For example, there's a shoulder usually there, and finding that shoulder using CodeCarbon to figure out if I throw this fraction of a kilogram of CO2 at this problem, I'm actually going to get a lower accuracy than if I had stopped beforehand. So using a tool to figure out, where that is, I think is very helpful. And so just being aware of the impact of it and trying to maximize for accuracy and not just energy usage.
Right. Yeah. One of the things you called out is more energy, which means more emissions, is not necessarily more accuracy.
Yes.
Yeah, adding on more practical solution. For example, when you're doing a hyperparameter search, which is basically you doing the combination of numbers of variables and try to find the best combination to get the best results, the best more precise model or whatever metrics you're optimizing for, you will likely most of the machine learning libraries have an option to do early stop. Like instead of doing training your model for 4 days for all hundreds of and dozens of combinations, you train 10 of them for 1 day, and then you see how it evolves. And if you take only the 2 best of them and try again, you can reduce your training time and emission by a lot of percentage. And on other protocol, you can also move all the code that doesn't need GPU to run something somewhere else, like for CPU, then you store it on disk. It's still emitting less emission than not using the GPU on your server, and try to use your GPU better, even by training more model on the same GPU, or changing your model to be more efficient to train in less time.
And one of the things that we've also advocated for, and it can sound a little naive, but as Jonathan said earlier, like this field has been moving fast, is to publish and be transparent about those things. And I think if the community shows interest and shows that it is one of the broader impact features that they look for when they think about the systems they create and deploy, I think it's also something that can spread in other areas than just your very specific niche of research. For instance, I'm thinking about the research community here, but because that's my environment. But I think it's also the case in the industry.
Yeah. Another thing that you all talked about is if you're computing locally, so maybe at your university or in your house these days, that's probably where you are. You know, the local energy infrastructure matters, right?
It does. It does. Like, for example, Quebec has an average of, like, I think 20 grams of CO2 per kilowatt hour or something, which is probably 40 times lower than some other regions. Like, you can check the, well, no, because Quebec doesn't share the data with electricity map. It's a shame. But you can see other, like, if you just compare the results in Europe, for instance, and you look for France, which is
like France versus Germany.
Yeah, it has a nuclear electricity grid, mostly France, right? So if you compare France to Germany, it's going to be very different. But
95% low carbon. That's well done, France. Good job, Boris.
But even if you click on Germany, what you'll see is you might have a time series somewhere for the last 24 hours.
You at least have this nice breakdown over here.
You have that,
right. You can move it over. So there's your time series.
Right. So you can even see that during the day, it's not the same. And just like your electricity provider will charge you differently for different times of usage, like high demand or lower demand times of the day. And like carbon emissions are also going to have that kind of variation that you could care for.
Yeah. One thing I wanted to give a quick shout out to, I don't know about different locations. Here in Portland, one of the options we have is to choose a slightly different energy choice. If we pay $6 more per month or $11 as a small business, it will basically be wind and solar. And if your local grid offers something where you literally pay $6 and it can dramatically change it, like, do the world a favor. Opt in.
Yeah, we have the equivalent in France also.
Same in the United States. There's a patchwork of different state laws that mandate that these options are made available to people. So yeah, definitely take advantage of it.
Yeah. Yeah, it literally is a checkbox. Do you want to have this, yes or no, and a small fee? And they probably, honestly, probably what's happening when you check that box, like some of that energy would have just gone to the general grid, and now it's promised to you. But soon as enough people check that box to go beyond the capacity, then that's going to be an economic driver to make more of it happen, right? So hopefully we can get there. Although I suspect data centers are where the majority of the computation happens.
Yeah.
Yeah.
But it doesn't, I'm not backing this by any knowledge here. I'm just, it's just my personal perception, but I feel it's like, it's too little. Like this is too cheap. How come like it's so cheap, right? So many things in our daily life should actually be more expensive if we knew how much energy and resources and how much they cost the environment, right? So it feels like it's a no-brainer when it's so easy and it's so cheap in this case, but like how many other areas of our daily life and consumptions have those those
Would you
paths
pay
was, like,
3 times as much to fly, right? Would you pay $3,000 to go from France to Portland rather than 1,000 or whatever, right? That's a harder thing than checking a $6 box. Yeah, and
Yeah.
probably a harder to solve a problem. But luckily, we're talking about computers and ML and not air transportation, so don't have to solve it here. We'll do that next time. Speaking of solving it here, what's next? Where are the things going for you all in the future?
So I'm a PhD student at MILA in Montreal, so it's Quebec's AI Institute. So I feel like I'm going to stay there for at least 2 or 3 more years until I finish this PhD, and then we'll see.
Yeah. But the other two, where are you going with this project?
Oh, that was about the project. I'm sorry, I missed the point.
Also, yeah.
Yeah, I think that we've got some things on the horizon. One is that the other part, sort of under the hood, that's kind of complicated, is deriving the energy mix and getting the CO2 intensity of the energy grid from the energy mix. So figuring out, okay, if you have X% natural gas, X% coal, and X% oil, how does that translate into CO2 emissions? And we have that's actually an extremely complicated problem to answer, because we have different chemical compositions of coal around the world. For example, coal that comes out of Kentucky has a different CO2 impact per joule from combustion than coal that comes out of Wyoming, for example. So we've got all these different layers to figure out.
For oil, you've got like the oil sands of Canada versus Saudi Arabia or whatever, right? Okay.
Exactly. Yeah. And these and all of these sort of chemical differences, matter, and they reflect different efficiencies. And that's not even getting into the difference in hardware in different power plants. So what we want to do is we want to actually dive in a bit deeper and get at some of these regional differences in carbon intensity and plug them into the data set here, so that we can refine our estimates as much as possible.
Yeah, and shout out to the cloud providers, provide more data, to the CPU providers, provide more hooks, things like that, right?
My hope for the project is that in few years we don't need this project anymore, because we are doing estimation, and there's better people in the industry, cloud providers and hardware vendors that are better suited to get more precise data. But until then, I hope that the project can help companies be aware of their mission, take action on that, and allow the project to be more precise and give some estimation range for everything we are measuring.
I feel like there are 5 to 10 companies in the world that can control all of the information you have. So we've got Intel, AMD, Apple for the chips. We've got AMD and NVIDIA for the cards, and Azure, AWS, GCP. Like, if they all provided more information, then this would be not much of an estimate, more of a measure. So a couple comments from the live stream. Corey Adkins says, thank you all. I've recommended this package to my ML team, which is awesome. And then
Thank you, Corey.
Ryan Clark says the efficiency varies widely between countries and whatnot, but you sort of addressed that already with your comment about like trying to work to understand the different sources and how they, even though they both look like coal, for example, they're actually not the same.
Yeah, it's a really great question, and it really is something that we've relied on data from the U.S. because we have the highest resolution of this and of the CO2 impact per energy consumed, and we have the most transparency about the numbers. It's not just a number, in a in the end of a report or a footnote of a report. We can actually trace it and do some due diligence on that. So we've used those numbers, but if anybody listening to this or hearing this has a connection with any of those companies, the hardware companies, or knows how to get more energy data, we are always looking for collaborators and contributors. So please reach out to us.
Yeah, fantastic. All right, I know we're pretty much at the end of our time together, so let me just ask you one really quick question. So I have a model I want to train. So I'm going to fire up a Docker image, maybe a set of them on Kubernetes. I'm going to kick them off, let them go do their thing. Then I'm going to come back next week, have another idea. Then I'm going to train up some more things. Maybe my colleague is doing the same. this is going to generate a bunch of emission.csv files. How do I correlate? How do I put these all together so that I can see, like, as a team, this month is here we are? Is that something that happens?
So it's I'm really glad you asked this question because this is something we're working on. So currently, I think you can just sum up those CSV files. I think
it's
that's
up to you track and like say, okay, here's when we're sending in from this run.
yeah. I mean,
Okay.
CSV files have a lot of downsides. It's less object-oriented, and you could have a JSON file that would be more structured and so on. But at least it's very easily.
It's super easy. I think it's
right. So,
I think it's totally good, actually. It's more about it's going to be
Yeah.
transient files in lots of places. How do I put them into one
Exactly.
place so I see it as a whole?
So-
Yeah.
So what we've been working on lately with a team of volunteers in France with the dataforgood.fr initiative is to create and deploy an API in a database. So we want to create this online storage of the time series and not just the final sum, and have that in a hierarchy of ownership from the organization to the single run through teams and projects. That requires a lot of work. That requires deployment, that requires fans and sponsors to host that thing. That requires a lot of engineering. And I'm glad you asked that question because I also wanted to have one word about open source and who's doing this. And it's all about volunteers. And no one is paid for that. Companies like Comet or the Boston Consulting Group, who've been a partner for more than a year, do dedicate some software engineering time. And we need more collaborations. And if you think this tool is great and you want to use it, I think we would really appreciate if some of you had time to help, because it's a small team of volunteers, and it's the same for most open source projects out there, and they need collaborators and contributors. And I think it's one of the things you can do also is help out. And most of it is pure Python, right? So chances are you're going to be able to help. Or if you don't know Python, there's some data collection issues, and it's just about writing to a CSV file. You just got to find the time to go fetch those numbers. There are data visualization issues to help improve the dashboard and so on. So like it's never ending. So everyone can help.
Yeah. Sounds like a really great project to get involved in if people are looking to find an open source thing to work on.
Yeah. And we're willing to onboard you, which also is sometimes
yeah, that's great.
bumpy in open source projects. And I think, it's hard, and there are hundreds of guides of how to contribute to open source projects out there. I think we want people. So like, we're going to help you help us.
Yeah, very cool. I encourage people to do so. All right, final quick question before we get out of here. Brian Hermson says, I know this would be a big ask, but I would love to see this as a built-in profiler for CPU-intensive ML libraries. Yeah, that would be nice.
We just told you CPU is super hard.
Exactly.
Yeah, I think this is going to go beyond what we know and can do. But I agree with you. It should be part of more decisions in computer science in general, and software engineering, and hardware engineering, and everything. But
all right, let me ask you all the final two questions really quickly, since there's three of you. If you're going to write some Python code, what editor do you use?
VS Code.
Me too.
Sublime. Sorry, guys.
Right on.
I used
That's
to be
all
a Sublime fan, but VS Code is good now.
I feel like a lot of the Sublime people have moved on to VS Code, but Sublime's still popular as well. Notable PyPI package, maybe some cool library that works with some of the things you're all interested in. Just quick, that maybe people haven't heard of.
I like Rich, which is a super flexible, colorful, versatile tool to print stuff instead of writing again and again the same quacky print functions.
They call it a
custom made.
TUI. A TUI, is that it? Do they have it in
Right.
here? A TUI. A
user
terminal
interface.
interface. That's right. That's so
Yeah,
good.
Yep.
It's
That's cool.
incredible.
Nice.
Yeah, and
nice.
I just want to also give a shout out to the computational open source libraries like NumPy, scikit-learn, and Matplotlib, Pandas, and so on, because like those things run the data science world, and it's all open source, non-profits, and it's a few maintainers, and they deserve a lot of the credit for the recent advances. They
definitely do. Boris or John, you either want to give a quick shout out to anything?
If I will do some shameless marketing, I would say the CodeCarbon Python SDK, but more, I would say as our first API or some basis library that everyone use, request, and even just the Python standard library. I know some CPython core developer that are doing a tremendous job. It's a thankless job, so thank you to
for sure,
to them.
Yeah, everything Boris and Victor have recommended are great stuff.
Yeah, fantastic. All right. Well, final call to action. People out there are listening. They're doing machine learning. They want to be able to use this to measure their work and maybe make some change. What do you say?
Use it, contribute, evangelize, share. I think most of the thing you can do about climate change is spreading awareness, discussing those things, and challenging the status quo.
Yeah, fantastic. All right, Boris, Victor, John, thank you all for being here. It's been really great to have you.
Thanks so much for your time.
Yeah, thanks for having us.
Have a great day, everyone. Well, or evening if you're in France.
Exactly. Bye all.
Bye.